Welcome. In this video, I'm going to go over some questions from assignment 4. All right, so the first question. This first question right here is star closure. So it's basically every combination of A's and B's that you can make. And so the complement of this language would then be the empty set. All right, question number 2. So you have two languages. You have your first language is this one right here, and the second language is this one right here. So it wants you to take these two languages and make a regular expression for the union of L1 and L2, star closure of that union concatenated with L2. So this right here is L1, this is union, this is L2, here's the star closure of L1 and L2, and then we have concatenation with L2. And I believe this one you already had the solution for, so it's pretty straightforward, but there's an explanation. All right, so this next one show that if a family of languages is closed under union and under complement, it must also be closed under intersection. You can use De Morgan's law to show this, and this has already been covered, so this is a good example of showing how to use De Morgan's law for this. Use the construction theorem in 4.1. So this is just a practice. You want to practice doing intersection. To do intersection, you do the cross product. So I'm going to construct a DFA for this language, construct a DFA for this language, and then do the cross product. And then any that are accepting in both would then be accepting. So then you would end up with a DFA for the intersection of these two languages. Now, you can, if you have a DFA, you can also make NFAs, but for Theorem 4.1 and the practice that we've done in this module, we've used DFAs, so I'm going to use DFAs. And right here, okay, so let's get started. All right, so let's construct a DFA for the first language. The first language is a single A, so you can have a single A in that language because of the stars here, followed by any number of B's, followed by any number of A's. So a single A is accepting in this language. So if you start out with a B, you can have you must then if the first string in your if the first symbol in your string is a B, it is not going to be accepting because each string must begin with an A. So you must begin with an A. So then if you have a B, you're going to go to the trap state. Then once you get your A, you can have any number of B's followed by any number of A's. And then if you get a B after that, you would go to the trap state. So let's now do the second language. These are the transition functions for this language. So you can take a look at that. Q0, just Q0 with an A goes to Q1. Q0 with a B goes to Q3, etc. So these are the transition functions, and I write out the transition functions because it's much easier to create the cross product when you have the transition functions right in front of you. And also it's easier to do it when you have a complete DFA. All right, so this next one is any number of A's followed by any number of B's followed by a single A. This is not complete. I mean, I could put a lambda transition, but I decided to do a DFA to make it complete because it's easier to create the cross product that way. So we have to fix a few things. So we've defined, you know, the path right there, any number of A's followed by any number of B's followed by an A, but you're not required to have any A's and you're not required to have any B's in order to have accepting. So you could have any number of A's, or you could just have no A's, no B's, just one single A. But once you do get that one single A and you're accepting, then if you get an A or a B after that, then you're going to go to the trap state. Also, if you start out with just a single B, which you can have just a single B, you cannot have just a single B. If you start out with no A's and you have no A's, but you have one B here, then you still have to pick up the A, because if you notice, there's no star on this A. So basically, this language begins with an A, and this language ends in an A. So we've taken care of that. The only thing we haven't taken care of is if you have just one single A. So you do need to change this one also to accepting, because that is the string one single A. So I have a complete DFA here, in which, well, it's not totally complete because I don't have a, oh yeah, it is. I have transitions A and B for P0, transitions A and B for P1, A and B for P2, P3. Yes, so these are both complete DFAs with their complete transition functions, and that way we can have a full cross product, but we only want to deal with accessible states, so we might not complete the entire cross product. But the first thing we want to do is notice that if they are accepting, the only way you're going to be accepting is the combination of Q1, P1, because they're both accepting, the combination of Q2, P1, because they're both accepting, and then we also have Q1, P3, and Q2, P3. So those are the only states that could be accepting, but they may not actually end up being accessible when we start doing the cross product. So now let's start doing the cross product. So to do the cross product of these two, we start out with the first initial state, Q0, P0. From Q0, P0, so from Q0 with an A, you're going to go to Q1. And from P0 with an A, you're going to go to P1. So Q0, P0 is an accessible state, and so we know that Q0, P0 is an accessible state, and we now also know that Q1, P1 is going to be an accessible state. So we can start to only deal with our accessible states. Q0, P0 is an accessible state because it's the initial state combined of the two initial states. You start there. Once you go to your first initial state, you're only going to deal with states that you end up becoming accessible. So from Q0, P0, we're going to go to Q1, P1. The combination of Q1, P1, which obviously also is going to be accepting, that's going to be an accessible state. And it's very obvious because the single letter A is accepting, the single letter A is accepting. So the single letter A is going to be accepting in the intersection of the two languages. Then we have Q0, P0 with a B. Q0, P0 with a B is going to go to Q3, P2. So Q3, P2 will be our next accessible state. So I've gone ahead here and highlighted all of the accessible states. There are some states that are not going to be accessible. So once you figure out that Q1, P1 is an accessible state, then you do Q1, P1 and find out where you get from there, which is Q2, P1. And then from Q1, P1 with a B, you get back to Q1, you get over to Q1, P2. And now our next accessible state is going to be Q3, P2. And from Q3, P2, we're going to get to Q3, P3. And then just keep going down from Q3, P2 with a B. You go back to the same state. Q2, P1. We already have Q2, P1. If you notice, it's already right here. So that's not going to be a new accessible state. Q3, P2 we already have, so that's not a new accessible state. But Q2, P3 will become a new accessible state. Q1, P2, we already have that accessible state. Q3, P4 is a new one, Q2, P4. So these are all the accessible states. Q0, P0, Q1, P1, Q3, P2, Q2, P1, Q1, P2, Q3, P3, Q2, P3, Q3, P4, and Q2, P4. So that's not the complete cross product. We only in the end will end up with a DFA with 1, 2, 3, 4, 5, 6, 7, 8, 9 states, which the cross product of these two would of course make more than 9. So you don't need to worry about any states that you never get to. And that's why they're highlighted here. All right, so I went ahead here and just broke them up. Those are going to be our new states for our new cross product DFA. And then of course, if they are accepting in both, I've highlighted those that are going to be accepting. So you will notice that Q1, P1 is accepting. So in our new DFA, our cross product DFA, we will have Q1, P1 as accepting. We will also have Q2, P1 as accepting. We will also have Q2, P3 as accepting. But if you notice, Q1, P3 never ended up being an accessible state, so that's not going to be one of the new states in our new DFA. So this, take a look at this, how this was done. You just start out by combining Q0, P0. You look at their transition functions here, Q0, P0 with an A goes to Q1, P0 with an A goes to P1. So Q1, P1 will then become another state in our DFA. We're going to have the transition from 0, 0 go to 1, 1. Then 0, 0 with a B, you're going to go to 3, 2. Q0 with a B goes to Q3. P0 with a B goes to P2. And then you just continue on and you only deal with those states that you actually get to and become accessible states. This was an exercise in Module 4. This is the same thing, just different languages. All right, so now we've come up with our states, so now we can draw our new DFA. I'm going to replace, instead of writing out Q0, P0, I'm just going to put the 0, 0. So this is going to be state 0, 0, this is going to be state 1, 1, etc. So from 0, 0 with an A, you go to 1, 1. We've already determined that 1, 1 is accepting because both Q1 and P1 are accepting. From 0, 0 with a B, you go to 3, 2. From 1, 1 with an A, you go to 2, 1. We also know that 2, 1 is accepting, so we are going to make 2, 1 also accepting. 2, 1 with an A, 1, 1, we're still in 1, 1. With a B, you go to 1, 2. Now we're going to do 3, 2. I'm just going in order right here. So far I've just done these 4 transitions. The next transition is from 3, 2 with an A, you go to 3, 3. 3, 2 with a B, you stay in 3, 2. From 2, 1 with an A, you stay in 2, 1. I'm on this transition right here. 2, 1 with a B, you go to 3, 2. 1, 2, now I'm up here at 1, 2. 1, 2 with an A, you go to 2, 3. We also determined that 2, 3, this is 2, this is 3, that one's accepting. So 2, 3. All right, so that's where we are right here. We just went from 1, 2, so now we're going to go from 1, 2 with a B, you stay in 1, 2. Now we're down here at 3, 3. 3, 3 with an A or a B, you go to 3, 4. 2, 3 with an A, you go to 2, 4. 2, 3 with a B, you go to 3, 4. We're right here, 3, 4 with an A, you stay in 3, 4. With a B, you stay in 3, 4. 2, 4 with an A, you go stay in 2, 4, and 2, 4 with a B, you go to 3, 4. So now this was our first DFA for this language right here is this one. For this language right here is this one, and then this is the cross product of those two, only considering the accessible states, and now we have the intersection of these two languages. All right, so now we have the NOR of two languages, means that for any string, the string is not in L1 and the string is not in L2. So you can see that the NOR means the union of the two languages. You union the two languages. If it's not in L1 and it's not in L2, then you take the union of those two and you complement that union. And we know that regular languages are closed under intersection. They are also closed under complement. So the core of two languages means that the string is not in the complement of L1 or it's not in the complement of L2. So you take the complement of L1 and you union that with the complement of L2. And again, you can see that regular languages are closed under union and complement. Okay, so this one, if L is a regular language, and so L is going to be whatever your, this is a regular language, whatever is defined to be, and then you're going to concatenate it with two symbols. So that's what this is saying here. It's saying R is a regular expression for L. So this is the regular expression for L, and S is a regular expression for any symbols in the alphabet. So if you take any two symbols in the alphabet, that's regular, that's finite, and you concatenate it with any other string that is regular, then of course it's going to be a regular language. All right, so this, you want to show if L is a regular language, then you want to show that if you concatenate any strings in L with any strings that are in the reverse of the language, then you can show that it's also a regular language. And we do know that regular languages are closed under concatenation, and they are also closed under reverse. So if you take any strings in the language and you can concatenate with the reverse of any strings, then any of those strings that are produced by doing that is still going to be a regular language, because regular languages are closed under reverse and under concatenation. All right, so this is shifting. So all you need to do, remember to show that a language is regular, all you need to do is create a DFA or an NFA with that language. And if you want to shift it, all you do is you move from your initial state, you move over to a new initial state. Obviously, if you have if you have lambda transitions from your initial state, then you'd have to change your DFA. Not your DFA. DFA is very easy because you're only going to have one initial state. If you have NFAs with lambda transitions, then you're also going to have to shift any of those multiple initial states. But shift is an operation that if you perform shift on a DFA or an NFA, just meaning you move your initial states over one state or states, depending if it's an NFA or a DFA, then it will still be a regular language. So yes, this is an operation on regular languages that will still produce strings that are regular, that are part of a regular language. So I just put this in here for you guys to, and I gave you the solution and everything, because in the next, starting after this first exam, in the next module, we are going to start learning about identifying non-regular languages. And I can just say right here that this is not a regular language. The reason it's not a regular language is because in this language you have A to the N and you have C to the N, and you can use the Pumpy Lemma, and the Pumpy Lemma says that if any regular language you have that's infinite, and this is clearly infinite, you can have any number of A's, any number of B's, any number of C's, because it's greater than or equal to 0. So in any infinite language in a finite number of states, you would have to have a cycle. And if you have a cycle, anywhere you have a cycle, you can add extra, you can pump that cycle. So if I said if I'm going to pump the cycle on my A, right? So if I'm going to pump the cycle on my A, I'm going to say I could get 6 A's, right? There's no way for my DFA or NFA to count how many A's I have to know and have the same number of C's. So this is not a regular language, and we will be studying this in more detail in the next module. All right, so this one is very interesting because it's just asking you to say if L1 and L2 are not regular languages, is it possible to union L1 and L2, and will it always not be regular? And that is not true, because you can remember that you could pick any two languages, and if you end up with this is a regular language. So if you took two languages and you said this is not a regular language because you can't count the number of A's and know that the number of A's are going to be less than the number of B's. Remember, you have a DFA or an NFA, and it can't count A's and then compare that to the number of B's. And here you would count the number of A's and have more A's than B's. So if you have one with less A's than B's and another one with more A's than B's, if you union those two together, you would come up with this language, and this language is regular. So this is just getting you started for the next module, which will be after this exam. So none of this will be on your exam, but we have been working so much with regular languages, and we want to start thinking about non-regular languages.